Today I'm going to focus more on 14 and 15. The next time we meet, we'll focus more on 15 and 16. It all really just ties together. But regression is a fairly popular topic. So to start with, and so I don't waste your time, my time, our time, I thought I could figure out, what do you guys know about linear regression? So really what I kind of want to start out with is just seeing, what do you know? What things do you know? We're going to write them down, and then if we already know stuff, we'll skip over those slides a little bit. We'll go a little faster, and then the stuff we haven't thought about, then we'll go a little slower. So just randomly call out, you don't even have to raise your hand, kind of take turns and be nice, but what do you know about regression? This is going to be a really long, boring lecture. Okay, so let's do this. What do you know about lines? Let's start with that. Okay?
Can you go to one?
Got a line. What do you know about a line? They have a trend. Okay. Okay, so I heard trend. Okay. So we're kind of looking at trends. I heard the word slope. And I heard positive and negative. So this one that I have has a positive slope. What would a negative slope be?
Downward.
Down, right? So there's a negative slope. See, you guys know things. And then this one would be no slope. Ah, the slope equals 0. So now we have an equation for a line. So what kind of equation do we have? What's your favorite way to write a line?
Y equals mx plus
The only thing you remember from algebra. Y equals mx plus b. So what does the m stand for?
slope.
The slope. What's the b stand for?
Y.
Y-intercept. See, look at this. Alright, so now I will tell you, we are going to make one little change. It's not a big change. I promise. So, y equals mx plus b. Because, so this works really well when we just have one variable that we're talking about. But we're going to get up to having multiple variables. So we can't just have mx plus nx plus qx plus... So instead of doing that, we're going to change this to b1x plus b0. So I just renamed. My m is now a b1. My b is now a b0. So nothing crazy. This is my slope. This is my y-intercept. So can I make that one change? Okay. What else do you know? What do we know about regression?
Independent variables predict the dependent.
Oh, okay, so we're just going to start. We have independent. Predicts. So in my equation, which one is the independent variable? The x or the y? X. X. Alright, so the x is predicting the y. Are there any other words you've used instead of independent and dependent variables? So we've got explanatory variables. Those are going to be your independent variables. All right, you got an explanatory variable. It's explaining things. And those are predicting things. We also have predictor variables. So that independent variable has several different names. The dependent, you may see response. All of these words are the same. And all of these words are the same. I like independent and dependent. SAS uses dependent and explanatory. Other textbooks will use predictor response. So they're all kind of the same thing. All right, it's all just about your X and your Y variables. They just call it different things. What else do we know about regression? We can throw correlation in the mix too. Right, because getting this positive slope means you generally have some data points. That's yeah, right? So R is our correlation. This is going to be a positive. It's going to be a pretty big number. We're going to have a negative correlation, and it'll be a pretty big number too. Here we don't really have any correlation. Maybe positive. And somebody said we could square that. You know what that's called? That R squared value? I wouldn't expect you to remember this one. It's not one of those things you remember. This one's actually, it's called the coefficient of determination. Maybe I've heard that somewhere, but no, I would not have ever expected you to know that. Right, I forget it until I teach this lesson, and you're like, oh yeah, that's good. Right, so it's the coefficient of determination. So what do we use that R squared for in regression?
How much variation is explained by the variable?
Okay, so this is the amount. And I have a slide about this, but since we're here, the amount of variability in our dependent variable, I'm going to use y, explained by our independent variable, x. So if we're creating a regression equation, do we want R squared to be high or low? Do we want to explain a lot of the variability, or do we not? And so that kind of takes us back one step. What is the purpose of making this model, of making this regression equation? What are we going to do with it once we have it?
Use it to estimate future observations.
Yeah. All right. We're going to make estimations with it. We're going to make predictions with it. Okay. So if we're going to make predictions, do we want a good model or a bad model? We want a good model, right? So to get a good model, do we want to explain a lot of what's going on, or do we not want to explain very much? We want to explain a lot, right? So if we're going to explain a lot, then we want our R squared to be high. High is good. So we want a high R squared. And so our R squared, the other thing it's also known to do, this helps us with our model fits. Okay. So how well does the model, does the equation that we've created fit our data? And our goal will be, well, let's use one variable and see how much we can explain, how much variability we can explain. What if we added another variable? Does that help explain more variable or more variance, more variability? Or does that explain less? Does it confuse things? And so our goal over the next 3 weeks is going to be to create that best model. It's going to be, and I'll talk about this a little later, it's going to be a best model. It's not the best model, it's going to be a best model. So given our different modeling, you may have an answer, you may have an answer, you may have an answer, and you only have 3 different answers, but to you it's the best model for your given scenario, right, or for your given assumptions. So our goal of this will be to find a best model. And you'll actually see that for your homework assignment. Okay. So I'll ask you to find a best model. And if you're working with a friend, you may or may not get the same answer that your friend gets. And that's okay. Now there are wrong answers, but there's not necessarily a right answer. There are better and worse answers. And we'll talk about why and show you why one's better than the other. What else do you know about regression? I have like 3 empty slides, and we only filled up 1. That's a good start. So we'll start here. What do you know? So you know more than you thought you did. Blank slides. If you think about something, we can go back and add it. So today's a little more lecture-y, then we'll get into SAS. I didn't put as much SAS on the slides this time. We're going to do a little more interactive SAS today. And I really want this. So, big picture now. Sit back, relax. Let me talk action for a few minutes. Regression analysis, the big idea is we're developing some type of equation, a model, to show how variables are related. So chapter 14 is all about simple regression, so we're using one variable to predict another variable. Then we get into chapter 15, and we do multiple regression. We get more factors. That's another word we could use for our independent variables, factors. Okay, we get more factors, we get more predictors, we get more independent variables, and then we can generally get better estimates. Not all the time, but most of the time, if you're trying to predict a value with just one value, unless they're really, really correlated, maybe not. If you add a little bit more information, then you can generally get a better estimate, a better prediction. So the variable being predicted is the dependent variable. Variables being used to predict it is our independent variable. You already said that. For our regression equation, you guys already came up with this too. The difference here is we have our regression equation. This is our formal model. And when we write formal models and formal hypotheses, we use Greek letters. So our regression model is beta naught, beta sub 0, plus beta 1x, plus some error term. And in our model, we always have this error term on the end. Okay? Because we're not going to fit a line, a perfect line, unless there is an absolutely positive or negative one correlation with these two variables. And then really there's not much of a reason to create an equation. Okay, there's going to be some error. So your model in general has that error term. However, we're going to actually try to estimate given our data. And when we estimate using our data, now we don't have the error term because we're making an estimated equation. When we make the estimated equation, we use b's instead of betas. It's a fun quiz question, wouldn't you say? I love it. I say that word and like people's heads just pop up. Like, what you say? What you say? Yes, it's a good thing to know for quizzes, tests, which one is a actual model regression equation and which one is your estimated regression equation. The other tip, this one is a y and this one is a y hat. That hat makes it a prediction. This is kind of like our symbol. So if you weren't given the betas and the b's and you were just given some values, then the y hat is what makes it a prediction estimated equation.
This is like when we did not run this bad equation hypothesis.
Not necessarily that. It's just, here is the big picture model, how it's set up all the time. And in the estimated part, that's what we're actually going to plug our values in.
Wait, so why does the estimated equation not include the error term?
Because we're actually going to create based on our data, here is our equation. So we don't have any error because this is our equation. Now if we had different data, we would get a slightly different equation,
Right.
and then we have that estimated equation.
Right.
And then if we had slightly different data, we'd get another one. And so that's why it's an estimated equation. Whereas over here, this is the format that we're looking at for the model itself. So like this is your blueprint, if you want to think about it that way.
Yeah.
And here's your actual values.
So like when do you ever use that?
Just when you talk about it in general.
Oh, okay.
Also, isn't the mean of the epsilon 0 too? So the expected value of it 0?
Yes.
So
Yes.
this is like the equation for the population, and this is for individual samples, and when you bring the samples together, you get an epsilon.
Yes. That's a good way to say it. How you guys feeling about that? I love that you dig into the things and I'm like, oh, we're going to slide right over this slide. And you're like, let's talk about this. Yes. But no, I mean, this is important stuff. I love that you want to learn the math. I feel like I've been cheating a little bit this semester. So we've already talked about our regression models. We've got positive slopes, negative slopes. How do you know how you make regression lines? How it actually works? The big picture that we're going to focus on is we're going to use the least squares method. This is the most common method used in making multiple, either simple regression or multiple regression. And really what we're trying to do is we want to get that error term as small as possible. Okay? So visually, what we're trying to do is if we have, actually let's work this one here. If we have some data points, we want to try and find the line that fits them the best. Right, the best fit line. You have to print this. And the way we figure out which line fits the best is we talk about the actual observation. And then here, if you draw a line straight down, this would be our predicted observation. So here we have an actual observation. This is Y1. Here's Y2. And then we would have a predicted Y2. Those should be straight up and down. All right. Make it a little bigger. Okay. And we're trying to minimize all these little red lines. So from where there's a prediction to where the actual value is, we're trying to minimize all of these lines. So visually, that's what's trying to happen. Mathematically, we're taking our observed value, and we're taking our estimated value. Right, it's estimated, it has a hat on top of it. We're subtracting the difference, we're squaring that difference, we're adding it all up, and we're trying to find the line that gives us the smallest value. That's our big goal for our least squares method. Does that make sense? So if you were trying to calculate these things by hand, we have equations for the slope and for the y-intercept. Would you have to calculate things by hand? No. But if you wanted to, all it is just a series of independent variables, dependent variables, and means. Calculating the slope. We calculate the slope. It looks a little different than the formula you remember from algebra, but it's just a jumped up version. So the thing that I do want you to know is, what does a slope represent? Right, so think back to, let's not get the answer all the way away. So what does a slope represent? Let's start with easier. What does the y-intercept represent?
What the expected value is at a value of 0.
Yeah. So when x is 0, when we don't have a value for our independent variable, okay, when that value is 0, what do we expect to have? What is our estimated value? What's our predicted value? Sometimes that's meaningful. A lot of the time it's not. So like if I was to take this line and continue it on out, that might be meaningful, but a lot of times you're going to get negative values that don't make any sense. Okay. So your y-intercept doesn't always make sense, and that's okay. What about your slope, though? When you think of slope, what do you think of?
Relationship.
Relationship. Okay, what kind of relationship? A rate of change, right? A rise over run. Right? Those are kind of your common things. Okay, so when you think about a rate of change here, as we make a unit change in our x variable, then we have a slope change in our y variable. Sound familiar? I have this mix of like, yes, and the faces are very mixed today. So a 1 unit increase in the independent variable leads to an estimated slope increase or decrease, depending on if it's positive or negative, in the dependent variable. Why are these things important? Because these are the way that you tell people what's going on. Showing someone a regression equation may be helpful, maybe not helpful. Explaining to somebody that as you have a unit increase, then this changes your outcome. That's something that most people are going to understand. All right. The coefficient of determination, we talked about that. And it's that r squared value. It's the percentage of variability in our dependent variable that can be explained by the linear relationship between our independent variable. If we have an r squared value, because that's what ISYS will give us, and if we have an r squared value of, I can take the square root of easily, 0.25. Then my question is this the graph? Or is that the graph? Or do you know? You don't know yet. What do you need to see you can actually know? What if I told you, and I'm just making up numbers, these may not even make sense. Now which one is it? The one on the left or the one on the right? The one on the right. And why the one on the right?
Negative slope.
So I got a negative slope. Okay. So when you're looking at your correlation, so you're given this coefficient of determination, you're given this r squared. But if you want to actually realize which way the variables are related to each other, then you have to look at that sign on your slope. Excellent. So now a hypothesis test. Our big question is there a linear relationship? Okay. Well, if there's no linear relationship, then what do we know about the slope? Is there a slope? It's 0, right? So if there's no linear relationship, my slope's 0. And then if I have a linear relationship, then I start to have either a positive or a negative slope. So to test if we have a significant linear relationship, a start to a good model, we need our slope to be significantly different from 0. When we reject our null hypothesis, Okay, so our null hypothesis is that our slope is 0. We reject it, that means we have a slope. So there is a linear relationship. Just because we have a linear relationship, does that mean that one thing causes another thing? As we're doing a correlation analysis, as we're doing a regression analysis, what's one of the most common phrases you'll hear? Correlation does not imply causation. Right? I was watching TV last night while I was grading. The grades get higher when I do that. I was watching TV while I was grading. I don't even know what was on. It was just like whatever was on TV. And it was like this law show, kind of, I don't know. But anyway, I popped my head up because I was grading the slides for this, and they're talking about correlation does not imply causation. Like, he actually says that on primetime television. I almost wanted to make you watch the clip of it just because it was that perfect when I was doing it, but I decided I probably didn't want to do that. So what we're going to do is we're going to have a test statistic, okay? Just like we've had before. For simple linear regression, when we just have one variable predicting another variable, we have a t-test statistic and an f-test statistic. And no matter which one you use, they're going to give us the same conclusion. That's going to be different when we start adding in more variables. So what we're going to have is our null hypothesis is that our slope is 0. So if we were to write this out in words, we could say that our slope is 0. Or you could say that there's just no relationship. And remember, this is going to be a linear relationship. Okay, so our alternative is that there is a slope. And so that there is a linear relationship. And so whether we use the t-test or the f-test, we're going to get this same conclusion. I'm not going to go into it too much here, because we're just going to jump into multiple regression, and that's where I really care that you learn this difference. Okay, so for right now, if we were to do an example, you can look at the T, you can look at the F, it's going to work out. Another fun thing we can do, let me ask you this. If you were going to give me a visualization of the relationship between two variables, what kind of visualization would you give me? Excellent. I've been drawing them all day, so yes, a scatter plot, right? So scatter plots are great when we're trying to look at visualizations here. So we have our visualization as a scatter plot. Our descriptive statistics are the correlation, the coefficient of determination. The next thing we've been learning in class is we can do confidence intervals. Well, you can do confidence intervals for regression as well. And there's two different types of confidence intervals we have. So we have a confidence interval, and it's going to be an interval estimate of the average value, the mean value for our dependent variable, given some value of x, given some independent value. Okay, so that's one thing. We have a confidence interval. We can actually get a confidence interval around a particular point. Or we have what is called a prediction interval. Okay, our prediction interval is used whenever we want to predict an individual value of y, or some new observation corresponding to a given value of x. So our confidence interval is going to look at kind of the average value. Our prediction interval is going to look for one specific point. Let's say that again, because I want to make sure I say it right. Our confidence interval is going to look for, on average, our prediction interval is going to look point by point. And I have an example of this to show you here in a second. So let's do an example. So we're just going to do some simple linear regression. So we're going back to Razorback stores. We kind of know surviving. We've survived the hypothesis test. We're going to go back and check out Razorback stores. Okay. So we've done a lot of stuff with Razorback stores. I figured we should actually use it. The first thing I'm going to look at is, can the number of items purchased predict the net sales? If I purchase more items, am I spending more money? Do you think that's a good, I mean, not very informative, but an okay regression to try?
Seems fine.
That's okay. Right, so first of all, if it doesn't make sense, then you may not want to do it. I mean, you want to have a good reason for putting variables into your equation. You don't want to throw variables in your equation just for the fun of it. Hopefully they should make some sense. Now, whether they're the best or not, that's a different story. So in our ISYS Enterprise Guide, I'm going to open up Razorback store data. And all know the path by now. Probably get there faster than I think. You can use either the dirty data set or the Thursday data set, the Thursday one. I think I'm going to use the Thursday one. Let me make sure that it has everything I need. Yeah. So I think I'm going to use the Thursday one data set. So it has all of our data cleaning that we've done, but instead of having it all in one crazy big program, it's just all right here, nice and ready to go. So what we're going to look at is, we're going to analyze our data. And you've seen this right underneath ANOVA, we have a regression. So really quickly before I do that, way back when we did descriptive statistics, you learned about the correlation. So if you go one down, you have multivariate. And the first option in multivariate is correlation. So I can do correlation real quick. In my analysis variables, the two things I'm going to look at is items. In fact, I'm actually going to go down and use my new variable. So I have new items and new net sales. Very much clicking, so I'll slow down for a second. I'm just going to do a quick little correlation. We can get this other places, but since we have, go ahead and look at this. The options, Pearson's, that's telling us that it is the linear correlation we're going to be looking at. That's the thing we're going to focus on. Here I'm going to create a scatter plot for each correlation pair. I don't need to do that because I just have one pair. Actually, no, let's go ahead and do that. Let's create a scatter plot for each correlation pair. I don't need my data, so I'm good to go. I'm going to click Run. We've got 1,000 data points, so it takes it a little bit. And so here we have a correlation between items and net sales, and it's only a 0.5 correlation. This has got 1,000 observations, about a 0.5 for the correlation, so it's positive. Most of it fits right here. The p-value here is teeny tiny, almost 0. It looks weird. Right, 39e to the negative 64. Basically what that's saying is take 39 and put 63 zeros in front of it. So it's basically 0. This gives you a 95% prediction ellipse. So when we're talking about kind of that prediction interval, this is kind of what's happening here. So there's our scatter plot. Now let's go see if we can do a regression. We'll get a trend line in here and see what else happens. So going back to my data, we're going to analyze. This time we're going to regression. So you have a HP linear regression. HP stands for high performance. You can play around with this if you want to. It looks a little bit different. It's got a few extra features. I'm not going to focus on that just because if you are using the tutorials, our tutorials are set up for just the regular linear regression. So I'm going to focus on that one, but if you want to go play with and experiment with the high performance one, you are more than welcome. So we're going to focus on that second linear regression. The data that we're going to use are dependent variable. So I'm going to try to see the number of items predicts net sales. So which one is my independent variable? Items. And my dependent variable, net sales. So I go back, my dependent variable, net sales. And here we call them explanatory variables. My independent variable is items. It doesn't matter. As long as you use new net sales, the math's going to work out. One's just how to visualize it differently. So it doesn't matter. So we have our data. So now when we do regression, right now we're just going to leave this as the model selection as the full model fitted. Okay, so there's no selection. In chapter 16, we'll start messing with this section. Okay, for right now, we're going to leave the model off. The statistics, we're not going to get into the deep dive of all the different types of statistics that you can have. Again, regression is one of those, so I told you about experimental design, right? You can take a year, a semester, a year of experimental design. Same thing goes with regression. You can take an entire course just on regression. An entire second course to really get into different regression techniques. So regression is a very big thing. We're going to spend 2 weeks on this. Okay, so you're going to get just enough to be dangerous. So this lets you do, this part up here is letting you do all of the math behind the scenes. So if you were actually going to be doing the matrix algebra to do the regression analysis, it provides some of that example for you. We're going to focus on just our full correlations. Here, these options kind of let you start breaking out different types of correlations, correlations in regard to other variables. We will play with the diagnostics, but not until 2 weeks from now. For the plots, right now it's just going to show you can do all appropriate plots and just see what it gives you, or you can actually come down and pick which particular plots you want. I always do the custom list, so it's going to give you the diagnostic plots, which we'll, again, talk about later. I'm going to click for now the scatter plot with the regression line. That's the thing that we're really going to care about. Predictions, we're not going to focus on predictions right now. You can. There's actually a video on your lesson 11 where Dr. Cronin does this. This is one of the things we're going to save for next time. So we will get to do all this, just not yet. I want to let you know it's there. You guys seem to like kind of know what's going on. So we'll get there soon. The titles, the properties, all that's fine. So now we're going to click run. So right now this is intro day. And then next week or the 2 weeks after, we'll get into details day. So what we have, I'm going to scroll down for a minute first. These are all these diagnostic plots. We'll focus on either end of today or the beginning of next time. Here is our scatter plot. The fit is this dark blue line right through here. The 95% confidence limits are this slightly bluer area around it. Okay. So remember, the confidence limit was the mean, the overall. So this is basically saying if we were looking at the lines and we made a whole bunch of different lines and different samples, this is our 95% confidence that this line fits within this area. Okay. The prediction limits, this is when we're talking about the individual points, and we're 95% sure that we're going to get a prediction value in between these limits. That's what the dotted lines are. So sometimes we're going to miss, but 95% of the time, the prediction variable value should fall in these dotted lines. Yes.
So 95% of the circle. Dotted line.
So it's still using the confidence interval idea. So it's not necessarily 95% of the dots. It's given any given dot, you have a 95% confidence of being within that limit. All right. So next we go to the data, the output. Right? So we have our null hypothesis. Is there a linear relationship or not? And so you'll notice here that our f value, and down here with our t value, we get the exact same answers as far as the level of significance goes. Okay? These two are going to match. The results are going to be the same. Okay? The values aren't the same, but the results are going to be the same. And so what we're trying to figure out, no relationship. Relationship. P-value is less than 0.0001. You want to go with our standard alpha, or you guys want to be crazy?
Any alpha is fine.
What do you want our alpha to be?
It doesn't matter with this period.
Not really. Doesn't matter. See, that's when it's fun though, so it doesn't really matter. So our alpha level can be 0.034. Your alpha level can be anything you want it to be. So our p-value is definitely less than our alpha level. We reject our null hypothesis. And we conclude that there is a linear relationship between these two variables. So even though the correlation is 0.5, so you're like, well, it may not be a strong correlation, but there's definitely a linear relationship. Our R squared value is 0.2457. So we can say, if I round 25% of the variability in our dependent variable, which one was, or sorry, in our dependent variables, which one was dependent? Net sales. Can be explained by the relationship between items and net sales. Totally doesn't have to. Everyone has some fun out of it. Just saw that free. Come on, you miss being under grass sometimes. Yes, I did. Oh, actually, I don't have to screenshot this one because I have it all typed out, but I'll screenshot it. So that's kind of what you're looking at. What questions do you have?
The R squared is interpreted as a percentage.
Yes. So I have on your slide deck these three things. So there's your correlation matrix. There's your observations. Oh, the one thing we didn't do, so here's your hypothesis test, your conclusion, your business conclusion. But the one thing we didn't do let's talk about the equation. Let's do that real quick. So where do you get the numbers to form your equation? Yes, lovely. So down here, these parameter estimates. So we're going to start with the intercept. I'm going to round to 2 decimal places because I'm talking about money. 7.74. And here when we just have 2 variables, it's fine just using x and y. Once we start getting into multiple regression, it's nice to put a subscript with what that x value is. I like to actually write out the word if possible. Some people will choose to do like x1, x2, x3, and then have like a little key for what those represent, just depending on the length of your equation.
I'm sorry for if you are. I remember you said this, but y hat, does that mean it's an estimate?
Yes.
Okay, thank you.
Yes. So because it's just given this 1,000 data points, it's just a sample. So our estimated equation would be $109.90 plus $7.74 for every item. So if we were to have some fun with this, land on this, what's this? What if we had no items? Right, we'd plug in 0 here. Does that make sense? And it kind of doesn't make sense, right? So basically, you're going to come in, you're not going to get anything, but I'm getting $109 from you. But that'd be great, right? Like just walk in the store, that's $109.90, please. Okay. So let's try one item. $109.90 plus one of these, $7.74. You did that, aren't you? What?
117.6.
6.4?
Yeah.
Okay. You guys are really good at this middle math stuff. So if you buy one item, then it's $117.64. So not knowing anything about my store, if I just gave you this regression equation, what would you say about my cheap store or my pricey store?
Pricey.
Yeah, my pricey store. Let's try, what do you think, 5 items? You guys think? $38.70. $148.60. Now I'm buying one item and I'm spending $117. If I'm buying 5 items, I'm spending $148. So remember, going back to how much variability were we explaining with this model? We're just explaining 25% of the variability with this model. So, is it a good model? I mean, are we liking, or we've tried some examples here. Does this seem like, would you feel comfortable saying, hey, if we can get, right, the way that you can extend this, if I can get 10 people in, and I can get those 10 people to buy 5 items, then we should be making $14,000, almost $15,000. You want to zero the right place? $1,400. That makes more sense. Whoa. $1,400. But even then, 10 people, $1,400. Think we can do better? try and do better. Okay, let's try and do better. So do you see how this is kind of working, how it's... Is this familiar? Are you comfortable with this? Okay. The next question goes to, so what? Right? We have this equation, so what? So since we added a little extra stuff, let's ask another question. So before we try and make this one better, let's ask another question. Can customer age predict net sales? What do you think about that one? That's your question? Okay. Let's try it. So, let me clear this off real quick. Alright, so I'm just going to modify my task. I still want to predict net sales, but instead of new items, I'm going to do customer age. So as long as you have age, any one of these, new age, new under age, whichever. So net sales and age. Everything else is going to stay the same. We're not going to change the model. We're still going to get our plot so we can look at it. Go ahead and click run. Huh. Now what do you think about doing age? And I thought it was a good idea. So for age here, we've got our line, our best fit line, that confidence interval, the prediction. I mean, we're just all over the place here. Right, we have an R square. Okay, so this doesn't give us the correlation. This gives us the R square. But still, we're predicting nothing. Right, 0% of the variability is being explained by age. So if we come up here, if we look at our p-value, what's our p-value? 0.23. So even if we went crazy and had an alpha of 0.1, we're still failing to reject our null hypothesis. I need to write all that out for you, or you're comfortable with it? All right, we're still on that. So we're going to fail to reject our null hypothesis. So there is no linear relationship. So should we use age to predict net sales? Not a chance. No, I thought it was going to be fun. Alright. So, obviously I was working on my slides last night and decided that screenshots were just not fun. So you'll see results here. So you could go out and you could go ahead and create a regression equation, and you could try to explain things, but it wouldn't make any sense, right? Because if we tried to create a regression equation, same kind of thing would happen. Y hat is going to equal 154.13 plus 0.1 for your age. So you're going to get 10 cents for every age older they are. Right? So what the slope tells you, a 1 unit increase in your independent variable, in this case age, so 1 unit increase in age gives us a slope increase. So for every year older someone is, we're going to hopefully gain a dime from them. There's no correlation. That's not really going to help your model at all. We don't want to use age. All right, your question.
This might be a very good question, but the probability here, given that there's absolutely no relationship as we can see, and even the R square is almost 0, why isn't the probability closer to 1? Why is the p-value closer to 1? Why is it still just 1?
Because of the sample size. Because since we have 1,000 data points, it's going to be harder to get our p-values farther away from 1. Because the ratio between the sums of squares for our regression and the sums of squares for our error, because the sample size is so large, when you factor that into the equation, it just doesn't let the ratio change that much. So if we had 5,000 people in our sample, it would be significant. Even with no relationship whatsoever, even as long as there was just a 0.001 correlation with 5,000 people in your data set, you'd still have a significant relationship, I bet. And it's all just the way the math works with sample sizes. And that's why this, so the way that we're looking at this right now, this is actually a great point. This is still the idea of we're trying to find a line that fits the data that we have. And the fewer data points that we have, the line is having to move a lot. When we start to have more data points, the line can get a little more steady. But then once we have so many data points, then it just reduces our values between, like the ratio, correct? So the F value is a ratio of what's happening inside and the noise in the middle. And so that value just gets closer and closer and closer to 1, even if there's nothing that's really there. So you wind up the noise of all of the variables winds up kind of counteracting what's going on in the model itself. So, that helps. All right, so let's try something different. So the number of items worked-ish. It was significant, but it didn't explain that much variability. Age didn't work at all. Before we go too much farther, let's talk about some assumptions that we're going to make. So in that model, and this was a question that was already kind of asked, in the model that we have, one of the assumptions we're going to make is that our error term is a random variable that has an expected value or a mean of 0. Right? So the idea behind our model is we don't want that error term. Right? The idea is to minimize the error term. We want our expected value to be 0. So that's one of the assumptions we're going to make. Another assumption we're going to make is that the variance of that error, okay, so the variability of that error, is the same for all values of our independent variable. So when we only have one independent variable, that assumption is not quite as important. When we start to have multiple independent variables, this assumption is going to be very important. Okay, so kind of like we had equality of variances in the past, that's kind of what we're looking at here. It's not really equality, but it's the equality of variances, but it's of our error term. We're going to expect our errors to be independent of one another. Okay, so we don't want error for one variable influencing the error of the other variable. So we have two variables that are too highly correlated, and they're both in our model. And we've got error associated with both of those, so the error from one increases, automatically the error from the other increases because they're so correlated together. And then we have that our error is normally distributed, so it's just some random variable. Normally distributed is called a random variable, and that's kind of what we want to look at. We have some visualizations that we're going to look at. There's a lot of different ways you can do this. You can get into a lot of detail. I'm going to focus on just kind of like two visualizations that we're going to spot check to kind of look at our assumptions. So the first thing we're going to do is we're doing this thing called a residual analysis. You're going to get to do this on your homework assignment. You're going to get to do this on your final project. Again, I have like these key words and people's eyes just go, oh. Okay, so you will do this on your homework. You will do this on your final assignment. All the residual analysis is what I didn't tell you was when we were looking at this picture. And I was looking at the predicted value. Pink color. Oh, I don't mind. figure it out. So when I was looking at the predicted value versus the actual value, and this distance right here, that distance is called the residual. Okay? It is your observed value minus your predicted value. Okay? So that distance there is the observed minus the predicted. That's your residual analysis. Okay? And we're going to use that idea. So much of our residual analysis is going to be looking at pictures. We're going to look at our residual plot against x, our independent variable. And we're looking at a thing called the standardized residual plots. So assumption number 2, the variance is the same for all of our values of our independent variable. If this is true, which we want it to be true, our residual plot should get an overall impression of some horizontal bands. Okay. Going back and forth between standing up and sitting down. So we're going to get residuals. And so you'll have residuals above and you'll have residuals below. But ultimately, they should fit in kind of a horizontal picture. Okay. You want there to be just as many above as you want them to be below, and you want them to be fairly, well, we want them to be the same. We want them to be evenly distributed. What you don't want to see is residuals that look like this, that start kind of close together and then kind of branch out and kind of form this like cone-shaped thing. Okay. When that happens, then we've violated this assumption. So that's one we're going to look at. Oh, look. Good patterns. Okay, so we're looking for this right here. Here, this has more of that kind of cone-shaped thing. And here we've got a linear thing going on, right? So it's not working. So horizontal, black is good. Cone-shaped thing, our variances aren't the same. And if our residuals are doing something funky like this, then we shouldn't be doing a linear regression. Okay, this is kind of tipping us off to, linear is not the way to go. There's probably some curvilinear thing going. There's something weird going on with our data. Okay. And so we're going to just look at it. It's just a visual inspection. Okay. We don't have any values that we're actually going to look at for right now. The other thing we're going to look at is our standardized residual plot. This is our assumption number 4. So the error is normally distributed. So if it's valid, then really what we're looking for here is that we really shouldn't see any pattern whatsoever. Okay, they're coming from the standard normal probability distribution. We really just shouldn't see a pattern. So if we have an observation, and it has a standardized residual value that is less than -2 or greater than -2, this is one of the ways we can find outliers. We haven't really talked about the influence of outliers. We will a little bit. But outliers can make a big difference in a regression analysis. Right? Because we're trying to plot a line of best fit through all of our values. And if we have one value that's kind of weird, kind of out there, it can throw off our regression line. So if we're looking at our residual values, okay, we've standardized them, kind of think z-score. Right? We've standardized all these values. If something's greater than -2 or less than -2 or greater than +2, then we're going to consider an outlier. So again, we're kind of looking for that, does everything fit in here? Okay, so if we had a residual that was out here, we would consider that an outlier. So there's not really a pattern, it's just kind of all hovering in the middle. Not really a pattern, nothing too high, nothing too low, so we're kind of happy about that.
And these are plots of the basically observed value minus the predicted value.
Yes.
That's what they're doing.
Yeah. So it's the observed minus the predicted, so that's the residual point, and then we plot that. Because we don't want the idea, right? If we're trying to minimize our residuals, right, or doing our least squares method, we're trying to minimize all of that error. So we want the same error above, and we want some error below, And we want it to be about the same distance roughly. We don't want anything crazy. So if we look at, and so this is where, apparently I didn't insert the residual plot. So if we go back to net sales, and this is items trying to predict net sales. So here are the diagnostic plots. Okay, so there's a lot of different things that we have. So here we have the residual versus the predicted value. Okay, that's not going to help us out too much, so we can use that. We'll talk about leverage in a little bit. If you look at the quantile plot, we can look at that one. So this quantile plot, what we're looking for is kind of a straight line. I haven't talked about this one. I have a slide about it here in a second. Okay, we're looking for a straight line. And this one's pretty straight. It curves a little bit at the ends, but for the most part, it's fairly straight. I can try one. We have, again, predicted value versus net sales. So here we have the predicted value versus the residual. Here's our predicted value versus our actual values. And then here we're talking about, do our residuals come from a normal distribution? We can look at this picture here. Do the residuals look like they come from a normal distribution? Yeah. We're okay with that. I'm still looking for, I have a residual plot that I want to show you. So if we go back and modify our task, so this is where, when we're looking at the plots, this is where you can pick which plots you want, right? So we have a histogram of the residuals, that's not going to help us. We already have the residuals by the predicted. So most of this is what's over here. What I want to check is right above the scatter plot, I want to check the residual plot. On this one and see what it does. So here we have the residuals versus our independent variable. And they're not great. We have a little bit, right? So this is, so we're trying to kind of look at that horizontal line. It's not quite horizontal. We have this little bit of curve right here that we might be concerned about.
So can you explain what it means that it's like plotted against the new items? Like the residual? I guess I'm just confused.
Right. So the new items, so across the x-axis, this is just how many items we have, right?
Right.
So if we have one item, then here's all the variables. And this is the easiest place to get lost in the weeds. So here's one item right here.
Right.
And so for one item, really what it looks like we're doing is that we are under-predicting what's happening here. Right? Because if you're thinking about a residual, the residual for this generic picture, right? So here we're actually over-predicting. Or sorry, here we're under-predicting. Right? So here's our predicted value. Here's our actual value. So if the actual value is above the line, then we're under-predicting that value. Here, our line is above the actual value. So here we're over-predicting. Okay. So here we have a, so think about this. So here's 0, 5, 10, 15, right? So here this difference is it's the observed minus the predicted. So observed minus predicted, here we have a residual of +5. Here, observed minus predicted, here we have a residual of -5. So our over predicted goes up here. Oh, sorry, I have it backwards. And this is where the positive and negatives are a little weird. So our under predicted, these guys go here. Our over predicted go here. And that makes more sense, right? Because with our equation that we had, we were kind of over predicting the price that people were actually paying if they bought one item. And then if you bought 2 items, we did a little bit better. We were over predicting and under predicting closer to half. Right? When we got out here to the end, we were under predicting a little bit. So people were spending, they were purchasing 15 items, and we were under predicting how much they were actually spending. So that's kind of the idea of the graph.
Okay. Thank you.
Yeah. Brandon, the hands go up. Yes.
Well, isn't that graph the same except for the scale? Same as, like, if you were to do.
I think it's the same as this one.
Without any residual or predicted value. So it'd be items versus just a correlation graph, would it be the same? Or like if you go down to the graph below that one, aren't they like the same graph pretty much? Just with different scales on the
Mm-hmm. They're very similar. I don't know if they're perfectly the same. They're pretty close, just with different scales. But the difference being, so it's really just kind of about what your question is that you're asking. Right? So if I'm asking, are these 2 things correlated? Then I can look at my net sales and my new items, and that's a conversation and a correlation that makes sense as far as the calculation of the correlation value. But if I'm just asking, how good did I do with my prediction? Because here we don't actually, I mean, we have a regression line, but that's not where our focus is. Here, if I'm asking how good did I do with my prediction, is there anything crazy about it? Then you can start to look here and see what's different. You have a different question?
Yes. That's more like SAS related.
Okay.
So we were saying like if it's above like two outside of that like residual,
Yes.
those lines, it's an outlier.
Yes.
So does SAS like in this case we're assuming that there's no outliers because 2 is not even plotted on there, or is that just like a setting? Or
So this would not be the graph that you'd use for that.
okay.
Right? So to do the outliers, you want to use
One in the middle.
it's not the leverage. I don't love that one.
One next to
What
it.
about the
Yeah.
quartile? Because you got like 0 to -2. You're like less than that one. I don't know.
So we'll have to, I'm trying to remember what they have for the R student. So these are your standard, yeah, so this one would be the one that I would use for my outliers.
So those are all just different ways to say the same thing.
There are different ways to say similar things,
Okay.
yeah. And this is the hard part where it's like,
There's just so many graphs in there.
there's so many things, right? So this would be something, and we could spend, if this is an area that you guys are interested in, we can spend more time the next Thursday or the next Wednesday on the diagnostics piece. This is one of those that, in general, I would probably spend about a month in my regression class going over all these different types of diagnostics and looking into them and digging into them and seeing how do I use what. So for me, for what all we need, it's just a quick little scan of, so the studentized residual plots. So that would be this one right here. So we're going to check this one right here for outliers. And then we're going to check this one. I'm going to move it so it's going to mess up. This one right here to see if things are normally distributed. And those are really the two big ones that we're kind of going to look at. I'm not going to get into what you do to fix things. So really right now we're just kind of looking at what's going on. Is there something that needs to be of interest? If something's totally not normally distributed, we can talk about transformations, and we'll get into that. Again, just kind of, a lot of these is just going to be kind of like making you aware of it, and if it's something you're interested in, we can go farther. But there's a few more key things that I want to make sure that we cover that are going to be definitely helpful for everybody.
So for the outlier graph, what is the R student?
So the R student is the studentized range. So whereas we were using a normal distribution, this is similar to a normal distribution, but not quite. There's a little. So like here, so it's a standardized residual plot. Again, if you look at the back of your book, and you actually start doing the calculations, there's going to be the table that you want to look at. It's not the R, or it's not the Z, it's not the T, it's not the F, it's not the chi-squared, and there's actually a studentized. This is regression. We've got kind of some of the basics down. Now we're just going to kick it up to multiple regression. So a lot of these slides are going to look very, very similar. The only difference is instead of having one independent variable, now we can have as many independent variables as we want. Within reason. I mean, don't go crazy. But as many as we want. Okay? So the regression equation looks the same, but now instead of just beta sub 1, x1, now you add in another slope with another independent variable. And as many slopes as you want to, with as many independent variables as you want to. Okay? The idea of the regression equation, the estimated equation, stays the same. The criteria for making this happen is still the least squares method. It's a little more fun in terms of the math. Now you're going to use some matrix algebra instead of just nice plain algebra. Our slope, okay. Again, I'm not going to have that formula out there because you're doing a little more matrix algebra. Still doing the same thing though. It still represents an estimate of the change in our y, in our dependent variable, that corresponds to a 1 unit change. The thing that we're going to add in here is when all the other independent variables are held constant. Okay? So when we're interpreting this, we interpret the slopes one variable at a time. So holding all the other independent variables constant, a 1 unit increase in our independent variable leads to an estimated slope increase or decrease in our dependent variable. So this part's still the same. The catch is just now we have to hold all the other variables constant to be able to interpret a slope. So you don't want to interpret all the slopes together because then it doesn't work. Y-intercept still stays the same. Sometimes meaningful, sometimes not. Coefficient of determination, still there. We still have that R squared. The interpretation still stays there. The percentage of variability in our dependent variable, explained by the linear relationship, and this time it's going to be with all of our independent variables. The one thing that's going to change here, and hopefully this won't be as big of a deal because you never really use the R squared, what we're going to focus on is our adjusted R squared. So what happens is, as you add variables to your model, the adjusted R squares compensates for the number of independent variables that we have. So when we add independent variables, whether they're statistically significant or not, okay, it changes our prediction errors. They're going to become smaller and smaller and smaller. If that's the case, then our error becomes smaller and smaller and smaller. Our error becomes smaller. The effect of our regression becomes larger. So our R squared is going to increase whether it should or not. So just by adding a variable, any variable you want to, you're going to increase your R squared. So the adjusted R squared takes that into account. So that's what we're going to focus on. Here, for our hypothesis test, we actually have two tests that we're going to look at. First, we're going to look at our overall test. Okay. The goal is still basically the same. Is there a linear relationship? Is there not a linear relationship? Okay, between our independent and dependent variables. Our F test, our omnibus test, our overall test, is going to look and see, given all of the variables that we have in our model, is there a significant linear relationship between all of our independent variables and our dependent variable as a unit? Okay, that's our F test. It's our overall test. Is this a significant model? Then we're going to go down and we're going to look at our T test. This is going to be a test for individual significance. So overall, we have a good model. But in our good model, or may have a significant model, in our significant model, are each of the variables that we have added contributing in a positive way to that model? Okay. So we have a separate t-test for each independent variable that we're going to look at. So in the past, where we had the f-test and the t-test having the same conclusion, because we only had one variable, now when we have multiple variables, our f-test is for our overall. It's kind of like an ANOVA, right? All of our slopes are equal to 0, there's no relationship. Or one or more of our slopes are not equal to 0, so there's going to be some type of linear relationship. Our t-statistics, that's going to be the individual differences, and we're going to say, okay, slope 1, is it linear related or not? Slope 2, slope 3, slope 4. Okay, so we're going to do two different tests here. One of the things that I care about in this class is this idea of multicollinearity. And I really hate teaching this in this class, because next semester, I don't care about this. But this semester, I care. Okay. So what we're doing this semester, do I have a slide about this? I'm going to flip ahead for a second and find out the slide that I have. Well, because it's a really fun slide. I'll flip ahead to this slide. So what we're doing this semester is we're doing explanatory regression analysis. We're taking the data that we have, and we're going to try to find a model that fits that data as best as possible. Okay. And when we're trying to find that, the focus is really going to be on understanding the relationship between our variables and the data that we have. Okay. Statistical significance is important. The magnitude of the coefficients, right? The slopes. How big is the slope? How influential is it? The signs of the slope, whether it's positive or negative. Right? I care about things. I'm trying to explain things with my equation. I'm trying to explain how net sales are impacted. Okay? I'm trying to explain what's going on. That's what's happening this semester. Multicollinearity, that idea is that two variables are correlated with each other. And if two variables are highly correlated with each other, you don't want both of them in your model. Okay? I'll go back to that slide and we'll talk about it a little bit more. Next semester, assuming you guys want to hang out with me, data mining. Now I got really big data sets, and now I don't care so much about explaining what's going on in my big data set. That's not my goal. My goal is just to predict things. And I want to make predictions happen, and I want to predict things as best as possible. And even if these two things are correlated, if having both of them makes a better prediction than only having one of them, I want both of them. The goal isn't explaining what's happening. The goal is predicting what's going to happen in the future. Okay? So regression is that fun little, depending on where you're at, the assumptions that you make, and if it's okay to violate certain assumptions, makes a difference. So we're going to focus on the explanation piece. So this semester we care about multicollinearity. Let's go back and let's talk about it. So multicollinearity. The idea here is if we have independent variables, so first question, do we want our independent variables to be correlated with our dependent variable?
Yeah.
That's a good thing, right? If they're not correlated, then they're not predicting well, and they're not doing a good job of explaining what's happening. So we want our independent variables to be correlated with our dependent variable. Yes. But we don't want our independent variables to be correlated with each other. Because if they're correlated with each other, now is the impact or the influence coming from this variable or is it coming from this variable? Or are we double counting an influence? Okay. So if two variables are highly correlated, here your book uses 0.7 to be a high correlation, then we can't determine the separate effect of the independent variables on the dependent variables. Right? We don't know which one's making the influence. And if estimated regression is used to be predicted, then it's really not important. But really, as we're trying to do explanatory things, we should try to avoid including highly correlated independent variables. Now, how do you do that? You kind of just look. Right? You do some summary statistics on your independent variables, get a little correlation matrix, look and see are any of your independent variables highly correlated. And then one of the things about regression is that this is where that content knowledge becomes important. What variables do you include? What variables do you exclude? If you have to make a difference and you have to make a choice, if two variables are highly correlated, which variable do you keep? That's where all the practical stuff comes in. I've got two variables, they're highly correlated. This one costs $5 to collect per sample person, and this one costs $50. Which one do I keep? The $5 one. Okay. Right, if we're still explaining that these two things are highly correlated, we want to get the easiest possible to collect the data. Okay, and that could be what we have in our equation. We'll stick with that. We'll try. We'll see if we have any collinearity happening in our equation. Yes?
What is the correlation between the two independent variables? If the two independent variables are qualitative, not quantitative? For example, all the black cars are sedans and all the red cars are SUVs. How would we figure that out?
So that's going to be more of a data collection issue. Because as far as multicollinearity goes, it's only concern, I don't say concern, but it focuses on that value, that correlation value, so you're just looking at the correlation between two continuous variables. Now, the point you make is very relevant, and that's more of a knowing your data kind of thing, and being able to say, you know, if color makes a difference, right? So you may want to do separate tests on put red in or put the type of car, and if it winds up being one or the other, then you just have this observation of, well, it's either red or the type of car, but we don't know. And I don't think we can know without doing like this warrants further study into an experiment that way. All right. So we've already done items in net sales, and we did age in net sales. Do you think the number of items, if we add age, would that help us predict net sales?
I don't think so. Especially from last time, I don't think so.
Last time was really bad, wasn't it?
It was.
I don't think it will either. This was a good question. And then I changed the data, and now it's less of a good question. So, This is why we do things with SAS. Let's look at our data. We have, so right now we're focusing on continuous variables. So we can't use type of customer yet. We have items and we're using items. We're trying to predict net sales. Can we use gross sales to predict net sales?
No,
No.
I don't think it'd be very smart.
Let's ask two questions.
Okay.
Question number one, can I do it?
Sure.
Should I do it?
Because it's an obvious relation.
It's an obvious relationship. It is, so gross sales is a calculated field, with net sales. So no, so we shouldn't use gross sales. Let's see what else we have. So loyalty member, it's numeric, but is it really numeric? Right. So it's a numeric variable, but really it's a qualitative, it's a category, right? Could we try previous store visits?
Yeah.
Maybe. Could we do previous total spent?
Yeah.
Maybe. Okay, so we have a couple of things that we could try. Okay, so let's see what happens. So I'm gonna go back to, so this is where I have net sales and items. And I'm going to add previous store visits. So I'm going down to my new section. I'm going to add previous store visits. So now I'm going to have two explanatory variables. I'm going to do this one at a time real quick. Nothing else changes. I'm going to run this analysis. So actually, let's take a step back. Let's take a step back. Keep this. We're going to come back to it. I'm going to go to my linear regression again. And modify the task. And instead of new items, I'm just going to replace new items with previous store visits. So I'm still doing another simple regression. So here, number of previous store visits, it is statistically significant. There is a linear relationship. We go down and look. I mean, there's a tiny linear relationship. Our R squared is 0.006. What's that make our R? Third of that. I can't do that one in my head. Point 0.25. So we have a 0.25 correlation. So not much of a correlation. Not really predicting any of the variability. We're predicting 6% of the variability. So it helps us. It is significant, but not great. What was the other one we wanted to try?
Previous time.
Previous spent. So let's take out previous store visits. And we'll put in previous spent. I don't think I changed that one. I think that's just an actual, just previous total spent. We'll run that. So right now I'm just saying, I'm trying to find that one single variable. I like this one. Let's go down here. Look at that one. It's a nice scatter plot. We have a significant relationship. And our R squared, 0.8. But wait a second. Hold on. Time out. We haven't really talked about this. What happened up here? You read those numbers? It says the number of observations read was 1,000. So how many observations do we have in our data set? 1,000. The number of observations used was only 535. So why did I not use all of my observations?
You don't have the previous visits.
Yeah, I don't have the previous visits, right? I only have previous visits on my loyalty customers. So really what this regression analysis did without me telling it to was it basically filtered by loyalty customer. Okay. So all we know about now are, if we're going to use previous spend as one of our variables, we can only talk about our loyalty customers. Okay, so that's something to kind of be aware of. Right? As you're pulling in your data, as you're running a different analysis, know what data ISYS is actually using. So I told it, hey, use the whole thing. And ISYS is like, sorry, I have to have complete data to be able to run a regression equation. Okay. So now if we're talking about only loyalty customers, it looks like total spend is a pretty good variable. All right. So now let's see what happens if we put all three of them in.
Wait, can you explain real quick, like the difference in interpreting R versus R squared? So like R squared.
Same interpretation.
Oh, it's the same.
Same interpretation.
Okay.
The only thing that changes is just that R, the adjusted R, is taking into account the number of variables and its calculation of how it's calculating it, and the R squared is not taking into account the number of variables that are in the model.
Right, but when we like.
When you interpret it and try to explain it to
but
me,
like when you squared the R earlier in the previous one, like to get like it was like 0.06, when you squared it was 0.25 or whatever.
yeah.
Right.
So
I just what's
Gotcha.
the difference between those two?
so R is the correlation,
Okay.
and then if you take the square root of R squared, that's how you get R.
Right.
So correlation, coefficient. This is the coefficient of termination. This one tells you just how correlated are the two variables. What is the correlation between these two variables? This one, so this, I don't know another way to say correlation. This is the percent of variability explained.
Okay.
And let's be careful. It's not that actual value. It is that value right there, that R squared. So R is just a correlation. It's just saying, telling you how these two things are related to each other. And it's on a +1 to -1 scale. The closer you are to 1, the higher the correlation. The closer you are to 0, the smaller correlation, just like you're used to. The R squared is all about once you have a model, and you have to have a model to be able to calculate the R squared. Kind of do. Then it's all about the percent of variability that's explained from the independent variable, or of the dependent variable by the independent variable.
Okay. Gotcha.
Are they both bound by?
So R squared is going to be from 0 to 1.
Right. Okay.
Technically, when you start using the adjusted R squared, it can get over 1, but really 0 to 1 is the practical limit.
And then R is -1 to 1.
-1, +1. Another question. Good question. All right, let's put all these things together. Okay, so I'm going to go back and I'm going to modify a test. So now I have new net sales. I have the number of items. We decided we could go ahead and add the number of new store visits. We've got the total spend. And just for fun, I'm going to add the age as well. I'm sure we'll take it out again, but we're going to add it. Alright, so here's all, basically these are all of our continuous variables that we could use. We're going to put them in our model and see what happens. And I'm going to click run. And just so I know where I'm at, I'm going to right click this real quick and I'm going to rename it. And I'm going to call this my linear, this is going to be my multiple regression. Just so I know. You don't have to, but just because we're running a bunch, I just want to kind of be able to keep track of them and go back and forth. So now, things that we have. I will take a screenshot of this when we're finished. So first we start out with our null hypothesis. Our null hypothesis is that overall, all of our, so if this is 1, 2, 3, and 4, all of our slopes equal 0. Right? There's no relationship. Our alternative is that overall, big picture, when I write out symbols, I'm just going to say that there is a linear relationship. So at least one beta doesn't equal 0. There's got to be a slope somewhere. There's our p-value. So our p-value is less than 0.001, which is less than our alpha level of 0.05. We reject. You guys remember like 4 weeks ago when you're like, what is she doing? And now you're like, seriously, is she writing that again? You've grown. I'm so happy. Okay, so we're rejecting our null hypothesis, so we get to conclude that yes, there is a linear relationship. Okay, so these 4 variables that we have are, there's a statistically significant relationship between these 4 variables and net sales. But are all these variables needed in our model? That's really the question. So now we're going to come down here, blue, and we're going to ask the question, is each variable have a linear relationship with net sales? Yes.
Because this is still including like the previous step, which is only looking at like the loyalty customers, is that something that needs to be mentioned in the null and alternative hypothesis or not?
So it's not in the null and alternative because they don't care.
Okay.
What does care is that when I'm talking about this,
Oops, caveat.
yes. So if you try to represent this to the boss, the manager, your team, as, hey, I found a regression equation for everybody. So it doesn't impact the null and the alternative. They'll stay the same no matter what your setup is. But should it be mentioned? Absolutely. I thought we had everybody. All right. So, for new items, we have a test statistic and a p-value. So for new items, do we reject or fail to reject our null hypothesis? Reject. There is a statistically significant linear relationship between new items and net sales. We already knew that, but now we're just confirming. Okay. Then we go to previous store visits. We have a t-value, and we have a probability, 0.0071. Reject our null, fail to reject our null.
Reject.
Reject the null, Linear relationship, yay. Then we go to previous total spend. That was what we really liked. It's still significant. Life is good, yay. New age. I'm gonna, so you can actually see it. Okay. So new age. Failed to reject. So is there a relationship there? No. So do we want it in our model? No. Okay. So here, so let's screenshot this one real quick. And so this right here tells us that we want to remove from model. No linear relationship. So let's go ahead and remove it. Let's get rid of this one. Yes.
We also want to check now whether there is a relationship between previous total receipts and previous total spend. Or do we do that later? Because those two independent variables are dependent.
So, and this depends. It really depends on who you ask. I don't know that there is a stated way to do it. For me, I prefer finding my model and removing non-significant values, and then I go and look at correlations for my existing model. Some people will do it the opposite way. Some people will look at the correlations first, throw out any variables that are highly correlated, and then put those in the model. So I don't think that order matters. I think it's more of a how you want to do it. So for me, I like creating my model first, because if I'm going to throw out variables that aren't statistically significant anyway, then I don't care about, oh, well, they're correlated. Some people will argue the other way, that it's like, well, no, you just want to look at the variables themselves and decide before you even start trying to make a regression model which you want. So this is going to be one of those it depends. From a explanatory perspective, now that you asked that question, I would actually probably start with the correlations and then build the model. From a predictive perception, I would start with the model and then look to see if anything's correlated. So it makes a good point. Yes?
In fact, to add to that, if the R square is relatively same for two, then it is more likely that they are correlated. Right? If the R square is so different, then it's probably that they are not correlated.
Yeah. I mean, that would be a fair assumption to make. If having that variable in the model greatly increases the R squared, then they probably aren't that correlated. And if it just increases the R squared, then they probably are correlated. Yeah, you can make that conclusion. So let's do exactly what he said, though. Right? So if we have these four variables that we want to put in our model, let's go back to our data set. And let's see, are any of them correlated? Let's check that multicollinearity thing. So to do this, I'm going to go ahead and go to the multivariate and do the correlation this way. I'm going to do multivariate correlations. And in this case, I want... Do I want to include net sales?
No.
You don't have to, right? It's our dependent variable. So if you want to know if it's correlated, you can. But really what we're looking for is our items, previous store visits, net sales. No, I don't want net sales range. Previous total spend, and age, the new age.
You need to validate remote, right?
Do what?
Validate remote the age.
Right, so if you want to take age out, I'm going to go ahead and put it in, just to show you that it's not going to matter. We know we're going to take age out. So you can either have age or not have age. I'm going to run this. And so here, it looks a little messy. So you have your correlation. the values underneath it, these are the p-values. So the second line, this is your p-value. And then your third line is your sample size. Right, so making sure that we actually have, so here, because everybody had age, we have a sample size of 1,000. But here we only have a sample size of 535. Okay. So if we really knew what we were doing, really we should probably filter by loyalty customer so that we actually have everybody using that 535 sample size. Okay. In this case, since we're getting rid of age, we're not going to worry about it. But these are the kind of things that I want you to think about and I want you to notice. Okay. If you're looking at correlations, you want to make sure that you're looking at the same number of correlations, or at least really close for everybody. So the correlations that we're looking at, we've got a 0.2 between items and previous store visits, a 0.45 between items and total spend. I don't really care about age. A 0.2 between previous store visits and previous total spend. And if we cared about age, age really isn't correlated with anything. Okay, and you'll notice I only have to look at like half of this. Because the information down here is just a repetition of what's on the top. So those are the things we're looking at. Nothing's correlated above a 0.7. So even though we have some that are correlated, they're not highly correlated that we need to worry about. All right, questions, comments? All right, so let's go back to our multiple regression procedure. So now we're not going to have to worry about multicollinearity. I'm going to go modify my task, and I'm going to take out age. And run it again. This time I am going to replace my results. So things that we're checking. Overall, I have a significant test. Items, store visits, total spent. Those are all statistically significant. I don't know what's happening to my screen right now. I'm kind of freaking out.
I'll wait.
Great. This is a little tricky, isn't it? So now if we go and we look at our adjusted R squared, we've got 8152. So about 82% of our variability is being explained by these three variables. We can write an equation. So we have our intercept of 56.53. We add on $1.75 for every item spent. We add on 55 cents, 56 cents, not correct, for every store visit. And we add on 7 cents for every dollar that they've spent in the past. So if I was going to interpret this 7 cents for every dollar they've spent in the past. Right? I could say it that way. Or I could say they've spent 70 cents, or that changes our equation by 70 cents for every $100, for every $10. Right? It's $7 for every $100. So when you're interpreting these slopes, what's all that in? Right, when you're interpreting these slopes in your paper and you're trying to explain things to people, you can change that unit to make it a more meaningful unit. Right? You're not going to change the equation, but as I'm doing this, I'm not going to say, hey, for every dollar they spend, you get 7 cents. I might. Or it might be for every $10 they spend, you get 70 cents. For every $100 they spend, you're going to get $7. Right? So all I've done is just modified my unit. Instead of 1 unit, I went to 10 units or 100 units. Okay, just to make things more understandable. And that's a perfectly fine and good thing to do. Okay. So we have an equation. We have, what else do we need to do? We're explaining a lot of the variability. So we're feeling pretty good here. Do you like this model? Is there anything else you want to try? We're trying to find a best model. You like this one? So as you're trying to find a best model, there are some things to think about. Best model. Take a screenshot of this one. Best model. One thing that we want. We need a low p-value. That's step 1, right? We have to have a significant relationship or the rest of it's not worth it. Okay, so we want a low p-value. Significant p-value. What's something else that we look at?
High R squared.
High R squared. We'll go ahead, just in case you take me literally, I adjusted R squared. Step 3, for the third thing we want for a best model, and 3 and 4 can probably be interchanged. Now let's do 3 this way. So the third thing that I really want you guys to do I see spelling this word. Parsimonious. Let's write it this way. Fewest variables. We want, so the idea, the law of parsimony is that the more simple the explanation, probably the better the explanation. Right? So why try to predict something with 5 variables if I can predict it with 2? Okay? So we want a low p-value, we need a high adjusted R squared, we want the fewest variables, and then the fourth thing that we need I know that sounds weird. We just want it to make sense. Right? And that becomes important. We don't want to predict gross sales, or we don't want to predict net sales with gross sales, or vice versa. Right? That doesn't make sense. Can we do it? Yes. Should we do it? No. Okay, we want to make sure that it makes sense. So here we have an adjusted R squared of 0.81, 0.82. We have an equation. We have all significant variables. This is a fine model. Right? We've already done a little bit of simple linear regressions. And did we like the previous store visits? I mean, it was significant, but it wasn't really helping out a whole lot. So what if we modified this task one more time? Here, wait, hold on.
Can you take a screenshot first?
That's what I was going to say, yes. Let me take a screenshot first. I got you. Wait. That one. New slide. Yeah. Okay. So we'll go back. Now we'll modify the task. I'm going to leave all this stuff because, so all I'm going to do is just take out previous store visits. Okay, so just based on what we know, we're going to take out previous store visits and I'm going to rerun this. So now, the question is, what has changed? So we still have a significant overall model. We still have two significant variables. So we've taken out, we took out visits. So now our equation has changed a little bit. Right? This is now $60. Here we're at $1.80. We're still at 7 cents per previous. So that stays the same. What's happened to our adjusted R squared? Hasn't changed much at all. So if I didn't have to keep track of their previous spend, that's nice. Or sorry, their previous number of visits. It doesn't really change. Now I have only 2 variables instead of 3. And we could even go that one step farther. We really didn't like the number of items. I'm going to modify the task one more time. Get rid of the number of items. Rerun this. It'll let me. There we go. So our equation has changed again, because now we just have the one variable. Our intercept's going up a little bit. The amount per spin really hasn't changed. Now we have an adjusted R squared of 0.8030. So we lost 1% of the amount of the variability we're explaining, but we're still explaining 80% of the variability. So if you had to pick between using 3 variables or using 1 variable, is that 1% an appropriate trade-off? You still want to know the number of items? Is it easy to tell the number of items? If you're talking about somebody just walking into the store, you have no idea how many items they're going to buy. But you could know how much they've spent previously. So maybe just a simple regression is just as good in this case as a multiple regression.
What about the residuals?
What about the residuals? What about them? Why do we care? So are we happy with, so let me ask that question. Do we want to do 2 variables or 1 variable? And we'll get to the residuals.
Do 1.
You want to do 1? This is what you get to decide on your homework assignment, on your final project. This is what you get to decide. Where's that trade-off? And that's why I say it's a best model. Right? So one person could argue that, no, I want to have 81% of the variability explained with 2 variables. Another person says, no, I'm fine with 80% of the variability explained with just the 1 variable. Did you have a question?
I had a question, but before that, I had to again, coming to this makes sense part, I feel that having the number of items really makes sense in this, even though it's only 1% explanation.
Okay.
Probably would want to have it.
So for your argument, you're going to say, let's do the 2 variables.
Yeah.
Okay. Somebody else, guy right next to you says, nah, I don't care about that. It's 1 variable. And this is the difference between you're the analyst. So as long as you can kind of explain and defend your answer, from my perspective, I don't care which one you do. I just want you to be able to explain why you made your decision. And so if I am, the person making the decisions, and being able to have that 1% more of variability can equate to millions of dollars, now I care. But if it's equating to hundreds of dollars, and I'm a $1 million, billion-dollar corporation, I don't know that I care. Let's make it as simple as I can, right? So that's why there's no the best regression model. It's just a best regression model. So as long as you can defend it, I'm happy with it.
Coming back to the doubt I had, see, for the previous case, there were 1,000 samples for items, whereas only 500 odd for the previous time because of the loyalty. I mean, do we really need to filter it, or I actually think since they are independent of each other, it doesn't matter that this can be 1,000 and that can be 500.
So the regression is only going to use complete data sets.
Yeah.
So even though we have the 1,000, the regression is only going to use the 535.
Oh, okay.
So it doesn't take 1,000 here and 500 because it has to have all of the data complete to be able to calculate a predicted value. So even though you have 1,000 for one variable and not 1,000 for the other, it only takes all that are complete. All right. So Jacob wants to know, what about those residuals? What about? Let's go find out. That's a good question. Imagine a picture of that. I did. That's okay. What you need from that picture is still there. That's the part we need. Alright. So if we scroll down farther, then we can get a look at the residuals. So do we have any outliers? We kind of got a few. So we haven't had this conversation yet. What do we do with the outliers?
Celebrate.
Yay! And in some cases, yes, that is the answer. Right? Next semester we'll do like anomaly detection. It's all about finding the outliers. This semester we're trying to predict stuff. No, we're trying to explain things. That's really what we're trying to do. We're trying to explain things. Explain the data that we have. So one of the things to consider is the outlier influential? When I talk about an influential outlier, most of our data is down here, and then I have an outlier up here. That's an influential outlier. Okay? Because where we would have had a line like this, when that outlier pops in, now I'm going to take my line and I'm going to I need to try to account for that. So it's going to pull that line up. It is an influential outlier. Right? You might want to get rid of that. Ooh, get rid of something. Okay. When I say get rid of something, we have 1,000 data points. If I could get rid of one anomalous sale, is that going to make a big deal in the overall grand scheme of things? Now let's say I have a classroom of 20 kids, and I get rid of one or two of those anomalous kids. Now that could make a difference, right? So depending on the case, you can either get rid of it, talk about it, explain it. Okay? If you have a lot of data, you can get rid of the anomalies and let everybody know. It's like, if this happened, this is what I did. right? You don't make a secret of it. But if you're still keeping 95% of your data, then most likely those anomalies are just that, right? There are a few anomalies, but I'm interested in explaining what happens with the vast majority of my customers. So those few people who are, yes, I had a couple of people who came in and bought the one really expensive item. Or I had a couple of people who came in and bought a lot of really cheap stuff because it was all on sale and that's all they bought. Right? Yes, that happened. But for my typical customer, right, for 95% of my customers, I'm going to make a regression equation based on that 95% of my customers. So I'm getting rid of the people that are above and below that are considered outliers, and that's okay. You sort the data, you filter the data, you can delete data. So here we have an influential outlier. Here, same kind of idea. We've got a whole bunch of people down here, observations. And then I have somebody up here. Is that an influential outlier? He actually fits right on my prediction. He's an outlier. I don't have, the majority of my customers don't fit that profile at all. But, fits my profile, doesn't really change my regression model much. So it's not an influential outlier. Right, so if they're not influential, then you can leave them in your data set. It doesn't really hurt anything. But if they are influential, then that's kind of where you get to look at things. And a lot of this is just knowing your data, digging in, seeing what's going on, seeing what's happening, and then deciding what to do. This is where keeping track of how you clean your data becomes very important. So, you have some outliers. And we scroll down a little farther. It's coming from a normal distribution, so we're happy with that. This is looking pretty normal to me. Those are kind of our three things that we check. So yeah, we have a few outliers, but that's okay. We got a mostly normal distribution, and this is kind of following the normal distribution here. When we look at our residuals, it's a little messy. We may have some issues with our variances, but nothing that I'm really concerned about. Alright, so questions, comments? Yes.
So that last graph that you drew where you drew like the dot that's technically an outlier, but it's on that line. Is the only way to determine that by looking at the graph, or is there like a number or like a slope of a point that you could tell like, oh, this could fall on mine?
So there's some other things down here with your diagnostics. This Cook's D kind of helps you out a little bit. Some of the leverage that you're looking at, some of these guys. So in the future, absolutely. If you want to get into this kind of stuff, there are more values for us. For us, I'm okay with just kind of looking at this and ballparking it.
If you want to measure the variability using the categorical variable, how do you do that?
You don't.
You don't?
Well, I take that back. You can.
Okay.
We got 15 minutes left. What if we had a categorical variable? Because so far we haven't had any categorical variables. We've only dealt with continuous variables. Right? So what if we wanted to add? So we found previous total spend is a good predictor, but we only know that about our loyalty customers. What if I want to know about every customer walking in the door? What else could we use? Items, significant but not that helpful. But what if I had items and something else? Right? So, let's see. So here's kind of the fill in the blanks of the things that I was doing. Categorical independent variables. That was perfect. Like, I didn't play for it all. She came with it. Alright, so categorical independent variables. What if we want to do that? What if we want to, so we're looking at our data set here. Data set. Right, we have the type of customer, we have their payment method, their gender, their marital status, right? So we know some things about them. Okay. what if that would help us predict how much they would spend? Well, let's find out. So a couple of things we have to do. So when we work with categorical independent variables, a lot of times, so like for our loyalty customer, right? I could have put loyalty or not loyalty, I could put yes or no, or I have ones and zeros, right? Well, so to do a multiple regression, you have to have a numeric variable. So you have to take a categorical variable and represent it as a numeric variable. And we're going to do a thing called dummy coding. There's dummy coding, there's effect coding, there's one more that you can use. There's different types of coding that you can do, and depending on the type of coding you do, depends on the results and how you interpret it. We're going to focus just on dummy coding. And all dummy coding is a sequence of zeros and ones to let us know if it's 1, that's the variable we're talking about, and if it's 0, it's not. But to do this appropriately, like let's say we have loyalty, right? We have zeros and ones, that's easy. We have method payment, or we have type of customer, 0 and 1. We have our marital status, we have married or single, 0 and 1. Okay, those aren't too hard. But let's say we're interested in type of payment, method of payment. Well, now we can't just 0 and 1, because we have more. We have our Razorback card, we've got a MasterCard, a Visa, a Discover. So we can't 0 and 1 that. Okay? And so the one catch, for when we're making dummy coding, or dummy variables, if a categorical variable has k levels, then we're going to have to create k minus 1 levels for a dummy code. So, let's see how we're going to do this. I already have it kind of set up. So for type of customer, and this part is essential, you need to write this down. You need to know what's the 0 and what's the 1. So if you don't know that, it's going to be really hard to interpret our equation. Okay. So type of customer. So here I'm going to have a regular customer is 0, and a promotional customer is 1. And let's just stop right there. Okay, we only have 2 minutes of class left. This is what we're going to start, where we're going to start next time. Okay. So let's do type of customer, regular 0, promotional 1. So let's go into SAS. So we have our glorious data set. We've done all sorts of things to it. Now I need a dummy code, a dummy variable. So we're all very familiar with our query builder. You thought you were done with it, but you're not. So back to the query builder. So we want all of these lovely variables. And now I'm going to add a computed column. And it's going to be a new column. And I'm going to recode this column. I'll click next. And what I'm going to take is I want type of customer. So I'm going to add. And I'm going to replace a value. So my options are, so I can type this in, or I come down here to add. Oh, hold on. I don't want to do type of customer. Just to make life easy, I'm going to exit out of this real quick. Because remember, type of customer had a misspelling in it that we already fixed. So I want new type of customer. So computed columns, new. I'm going to recode the column, and the column I'm going to recode is new type of customer. We're going to add this. I'm going to step through this kind of fast. So we're going to do promotional, and my promotional customer, I want it to be a 1. We're not going to enclose this value in quotes. When we enclose it in quotes, it makes it a categorical variable. We want a numeric variable, so we need to make sure we uncheck that. Okay. You can also come down here where it says column type and change it to numeric. So promotional is going to be 1. I'm going to go back and I'm going to add. And I'm going to select regular. And regular is going to be 0. Click OK. We have every everything we want here. We could specify a missing value if we wanted to. I'm just going to leave it as a missing value because I know my data is complete. I'm going to click next. Here I've got to name it something. So I'm going to name it, in this case, instead of new type of customer, all that, I'm just going to name it customer. And promotional equals 1. So just like a little note to me, so I remember that promotional is 1. I'm going to change down here in the format. It can't be a character format anymore. So I want to change that, and you can either make it numerical, or I'm going to make it none, just because I don't care what the format is. I'm going to click next. I'm going to run, so finish. So that's my new variable I'm going to create using our query builder. I'm going to close this. I'm going to run it. In 5 minutes or less, I'm going to show you what this happens. What happens. So if we scroll all the way to the right, we have our current, or our customer, where P equals 1, so 1's our promotional customer. So now, using this data set, I want to try and predict, so let's do regression. I'm going to do linear regression. We're still trying to predict net sales. Do you want to do it just type of customer? Yes. Okay. So this is kind of weird, right? So we're just saying, okay, so based on the type of customer, if you come with a coupon or not, this is what I'm going to assume. So I'm going to move type of customer over to my explanatory variable. Still have my full model? Yep. I want to use the customer, the P equals 1. No. Oh, new net sales. Yes. Yes. That's what I get for going fast. Yes, so new net sales. Explanatory variable is P, where the customer, where our P equals 1. So we've got those in our numeric, 1, 0. Our model's our full model. I'm going to go down here and go ahead and click the scatter plot just to show you how weird it looks. I'm going to click run. This thing. Well, so if we just use type of customer, is that going to help us predict net sales? No. So we can still go ahead and write an equation about it, just so I can show you what it is. It's not a good model. It's not a significant model. We should not use this model. But we could write an equation. So our equation here is going to be our intercept. And you'll notice this is about our mean, $157. So yeah, so if we don't have a good model, if we had to make a guess about what somebody would spend, just guess the mean. Does that make sense? Why don't you think about that one? And then we have our parameter estimate. So plus 191, X, and this is customer. So what we know is if customer equals 1, our promotional customer, then we would plug 1 in, and we would get y hat is 157.14 plus $1.91. If our customer equals 0, so if they're a regular customer, then we plug in 0, and we just get the mean. So when you have a categorical variable, what you have to do is actually plug in the zeros and ones and see how things work out. Okay, so in our case, if you're a promotional customer, you're going to spend about $2 more than if you're a regular customer. With a horrible p-value that we should never use this model. Right. But as far as the equation goes, that's like how the equation will work. So when we come back, we may do it next week after we finish our presentations. We'll finish this part up. And what you'll see is we can start doing the dummy codes for more. So we'll have to have multiple dummy variables.